Name is Alexander Korotin. I'm associate professor at Caltech and research scientist at IRI. And at this school, I will be giving two lectures related to modern generative models, modern generative AI. So today we have the first lecture, which I would say is much simpler than the second one. And most of you are probably even familiar with this topic because flow matching is the topic which is one of modern pervasive topics in generative AI, which is nowadays widespread. It is even more popular than diffusion models. But today, our lecture will be kind of preliminary lecture for the next lecture, which is much complex, much more challenging. And the second lecture tomorrow will be related to so-called diffusion bridge generative models, which are a special type of diffusion generative models specifically designed to solve certain data processing problems with generative AI. And let me begin. I will begin with very gentle and general introduction, but later we will come to more complex, even mathematical and machine learning concepts. Okay? So what is the plan of our first today's lecture? So first we'll begin with some just general overview of modern generative modeling, preliminary related to image generation and some related topics. Then we will briefly recall some basic aspects of so-called diffusion models. Today we actually are not going to talk about standard diffusion models, but we are going to talk about their extension or their, maybe better to say, particular case, which is very simple and easy and called flow matching. Yeah, so after brief reminder about diffusion models, we will go to flow matching and some its versions which allow to obtain different properties of the obtained generative model. Rectified flows, flow matching with general transport plans, and at the end of the lecture, I will talk about some extensions of flow matching, which are reasonable to know about, and next lecture we will discuss one of such extensions, which is called bridge matching. Okay, so let me begin with a gentle introduction. So of course all of you know that generative artificial intelligence is some kind of new appearing field. Yes, it's new emerging field, and a lot of things have happened in this field during previous 10 years. One of the main advances in this field is the appearance of so-called large generative models. Yeah, generative models for images and generative models for text like GPT and so on. So today we'll primarily talk about generative models for image data, yes, such as DALL-E, for example, and so on. And in this field, since approximately 2022, we have so-called large generative models which can produce new high-quality images which correspond to user for text prompt, for example. Yeah, such models, well, in Russia, for example, the most popular models are Kandinsky model by Sber, Shedevr model by Yandex, and also some other generative models like ChatGPT can also draw images by your corresponding to your text prompt. Yes, and nowadays this image generation in such models happens with very, very high quality. They rarely correspond to your prompt. And the question is, okay, how do these models work and how do they achieve this quality? Yeah, which technologies, which math lies behind these models? In fact, this field of generative AI related to images appeared not very long ago. It is a very early field, yes, because it appeared only in 2013, 2014 with the introduction of for first ways to do some kind of scalable data generation. Yeah, in 2013, 2014, it all started with the introduction of so-called generative adversarial networks and variational autoencoders. Yeah, which were the first generative models which managed to do some kind of generation of images. Yeah, so they managed to produce some very, very, very low quality, small resolution, grayscale images like MNIST digits, yeah, or TFD faces dataset and so on. But the progress goes very rapidly, and over the last 10 years, these ideas of generative adversarial learning, these ideas of variation after encoders have been advanced very rapidly, and nowadays in 2026, modern generative models for images, they can generate not only like very small images of bad quality, but they can even generate videos. Yes, videos of high quality. For example, I think many of you have heard about such models such as Sora, which was 1-2 years ago, and it was one of the first really scalable models which can produce video which corresponds to users' text requests. Yes, and the question is, okay, but why this field advanced that rapidly? Which technologies, which principles, which paradigms were behind this advancement? And actually, we're going to talk today about such paradigms. In fact, as I originally told you, it all started with introduction of generative adversarial networks in approximately 2014. Yes, but since then, a lot has changed in the field of generative models. First of all, one of the main concepts which actually changed this field was the diffusion models. So diffusion models is some other concept compared to generative adversarial networks, which has one very good benefit compared to generative adversarial networks, that they are much easier to train. Yes, and this fact allowed these models to scale very well, and most of modern generative models for images are based on concepts of diffusion models or their versions. Yes, and one of such versions of diffusion generative models that we are going to discuss today is the flow machine. But before discussing how this flow machine works, and let's discuss how diffusion models work. This will be a brief reminder. But even before this discussion, first let me try to a little bit formalize the actual problem that we're going to discuss today. Because I'm talking to you and saying that, okay, we're going to discuss the data generation problem. But what is this problem? Yeah, how to formalize it in terms of math, in terms of maybe machine learning, yeah, what we are going to achieve by solving this problem. Usually, one of the simplest problems in generative AI, which lies behind all this field, is the problem of unconditional data generation. Yeah, it is kind of the basic building block for which usually people design new algorithms, and then they scale these algorithms to high-dimensional data generation, such as text-to-image, text-to-video, and so on. How this problem is formulated? The problem is formulated in a very, very simple manner. So you have some data X, yeah, which is some high-dimensional data, for example, images. Yes, you have a data set, which is finite. And based on this data set, you would like to construct a model which is capable of generating new data, which is similar in its statistics to this data which you have, to this training data. Sometimes it's called empirical data, but at the same time it is new data, so it does not repeat your training data set. For example, in case of images, you would like to images of faces of people, yeah, you would like to generate new faces of people. How this problem is usually formalized? So this problem within the context of modern generative models is usually considered in the probabilistic sense. Yeah, because viewing this problem from the probabilistic perspective makes it much easier to work with using some tools from machine learning. Yeah, and formally this problem is stated in the following way. We assume that we have some data, and this data is not just some data. It is some data which comes from a known probability distribution of data, P star. Yes, so basically in practice we observe an empirical data set sampled independently from this unknown data distribution. And in practice the goal is to build a model based on these available training samples which will be capable of generating new data from this unknown probability distribution. So roughly speaking, we have some unknown data distribution. It is observable only by samples, and based on these samples we would like to build a model which will be able to produce new samples from this distribution. Yeah. Roughly speaking, this problem is called the unconditional data generation, because what you are going to achieve here, you are going to generate some new samples without any like conditions, just generate me some data which is similar to my available data. And diffusion models is one of the tools to solve this problem. Yeah, how do diffusion models work? Basically, this will be a very, very brief reminder. If you do not know like what is actually diffusion model, this will not be a very big problem for you, because today we're going to discuss flow matching, which is much easier even to explain than diffusion models. But to build a kind of bridge between like this preliminary problem of unconditional data generation and flow matching, it is anyway reasonable to recall what is the diffusion model. Yeah, basically diffusion models are generative models which work in the following manner. So suppose that you have some data distribution, yeah, and you have some samples from your data. So you would like to provide some procedure to generate new data from this distribution. How to do this? Diffusion models, they follow this principle. What is this principle? This principle is that you take your data, yes, and you provide some stochastic process, which is usually formalized in standard way, which gradually destroys the information of your data. What it does, it actually noises your data, so that at some point, at some very, very, very long time horizon, when you add a lot of noise to data, you can lose all the information about your data. Yes, and the main principle of diffusion models is to reverse this process of data destruction, yes, so that you will be able to just take some purely noised sample and then gradually, step by step, denoise this sample. From the mathematical perspective, what happens? You have some original data distribution, let's call it P0 or P star, which is very complex, high-dimensional data distribution. But what you do, you gradually destroy the information about your data, and at some point, your distribution after this destruction of information becomes very, very simple. So in the end, this noising process converges in the mathematical sense to some very simple distribution, some noise distribution, which is easy to work with. So you can easily sample random numbers on your computer, for example, yeah, from Gaussian distribution, for example. Yes, and the main point is, okay, I want to sample from this complex distribution, but I can't do it because it's just too complex. I have only data. Yeah, but I can sample from this distribution, and if I am able to sample from noise, and if I'm able to revert this noising process, basically reverse this data destruction process, then I'm capable of sampling from my true data distribution. And the main point of diffusion models is just to learn the reverting process, which reconstructs the information about the data. At the generation stage, this is used to generate new data. So we sample a point from from noise, and then we gradually kind of add more and more information by our data denoising process. From the mathematical perspective, this is usually expressed in the form of stochastic differential equations. So for the forward stochastic differential equation, which destroys the information about your data of some particular form, there is usually so-called reverse stochastic differential equation, which shows how basically to reconstruct the information about the data. And the main problem is that in this reverse stochastic differential equation, there is usually some unknown term, which is called the score function, and it is usually reconstructed using some techniques from score matching and using neural network parameterization. And if one manages to reconstruct this unknown term, then one may solve the problem of data generation, yeah, because he can model just the data generation process. So how data generation in diffusion models works? Basically, you need to just simulate this reverse denoising process. Yeah, so you take some original, so you take some noise, yes, and then you simulate this backward stochastic differential equation. How do you simulate this in practice? In practice, you usually do this using some numerical schemes. One of the most popular schemes is the Euler-Maruyama scheme, which is just the time discretization of this stochastic differential equation. So this stochastic differential equation is some just continuous time equation, and in practice it is just discretized. But there is one problem in diffusion models. Yeah, so when you generate new data in diffusion models, what you do? You numerically model this stochastic differential equation. And to model this stochastic differential equation, it requires some discretization level, so your delta time. And depending on this delta time, the quality of your model depends, because to accurately model your true stochastic differential equation, you need to do very, very, very small discretization. But why this is a problem? This is a problem because this numerical step of integration of stochastic differential equation is very complex, because when you go from some like noise point to, for example, next denoising level, yes, you have to compute this expression, and this expression, this thing which is called the score function appears, which is usually a very huge trained neural network. So roughly speaking, to accurately model your trajectory of generation in diffusion model, you need to do a lot of so-called evaluations of your neural network, which approximates the score function of the backward stochastic differential equation. And the problem is, okay, why not to take smaller, bigger, delta t, so that my discretization will be a little bit worse. The problem is that if you take higher step in this discretization, you actually obtain some error, and in practice you model not the true trajectory, but you fall out of it, yes? And then as a result, your point which you generate with the diffusion model becomes very far from the true point which actually should be generated. And this results in bad generation quality. So roughly speaking, in diffusion models nowadays, although they generate very high quality images, they do it very slow, because to generate new data, you need to very accurately model this stochastic differential equation by considering very small time discretization. And the problem is that to consider such discretization, you need to do many evaluations of your basic neural network, yeah, which is very complex. So early diffusion models, for example, in 2021, 2022, they required like thousands of steps of generation. So which means that 1,000 times you need to apply the same neural network to produce data from noise, which is very complex. And for example, this is not suitable for some real-time applications, yeah, on devices, for example, right? So people approximately in the era of 2022, 2023 started asking the following questions about diffusion models. Okay, we have diffusion model, and we have some trajectory of diffusion model which you need to simulate in practice, yeah? Why simulation of these trajectories is very challenging, yeah? Why do we need a lot of discretization steps? Because the trajectory is very curved, of course. Yes, this is obvious that if we want to accurately model this trajectory, then we need to do a lot of discretization steps. So people started asking the following question: can we design such diffusion models, or maybe some other type of models, in which these trajectories of generation will be straight? Why this is useful? Why this is reasonable? Because if you know that the trajectory of your model which you need to generate is straight, then you can model this trajectory in just one step. Because you will just know, like, the speed vector, for example, is the initial point, and you can just do a long jump, and there will be no error, yeah, because this is just straight trajectory. And this is one of the ideas which actually led to this concept of flow matching generative models. So now we start discussing basically the main topic of our today's lecture, the flow matching. First of all, what should I say before discussing this? That flow matching is not just yet another concept in generative models, like diffusion models, yeah? It is a very scalable concept, because in 2023, 2024, a lot of papers, scientific papers, appeared from large companies, large industrial companies such as Stable Diffusion, which managed to scale these models to real, like, production level. So one of the first scalable generative models for images based on flow matching were based on one particular version of this flow matching, and they were produced by Stable Diffusion company, which, as you may know, just produces different scalable models for data generation, primarily for like text to image. Yeah. So the concept which we are going to discuss today is scalable. This is the short message. But how it works and what is the difference with standard diffusion models, first of all. Yeah. So before discussing this, I should say that actually both diffusion models and flow machines that we are going to discuss today are a part of the same more general concept, which is called stochastic interpolance. We are not going to discuss this today, but if you are interested, you may just Google for some related papers. We'll focus just on difference between diffusions and flow matching. So in diffusion, what we did, yeah, we had some data distribution, we had some process which destroys the information about this data and at some point converges to some simple distribution, some Gaussian distribution, some noise distribution, yeah? And the training was to revert this noisy process. And all these diffusion models are based on the concept of stochastic differential equations. And what we are going to discuss today, the flow matching framework, is very related framework, but it has several differences from standard diffusion models. First of all, it will be based not on stochastic differential equations. So the trajectories which we are going to model will not have noise component, diffusion component. Yeah? They will be based on ordinary differential equations, and that they will see this in several slides. Because obviously, if you want straight trajectories, you need to somehow get rid of the noise component. It will be very, very hard to make some trajectory of diffusion to be straight. Yeah. Secondly, this framework is more general in which sense? In the sense that diffusion models, they model transformation of noise to data. But flow matching is more general because it can model transformation of arbitrary probability distribution to another probability distribution. Yeah. We are going to, we're talking about probability distributions on some Euclidean spaces of d-dimensional Euclidean space because images, the data which is the primary focus of our today's lecture, usually considered as like multi-dimensional tensors, RGB tensors, yes, and they are just embedded into standard Euclidean space. Compared to diffusion models, flow matching usually has a fixed time horizon because diffusion models, they usually have some guarantees of convergence when the time flows to infinity. Flow matching has just fixed time horizon, but this is just one technical thing which is not super important. Okay, let's move next. So first of all, the concept of flow matching appeared approximately in 2022, 2023. So this is a very, very fresh concept. Yeah. But as you may know, in AI nowadays, a lot of new things appear just every year. Yeah? So these are the main papers, especially the first two, which are related to this concept. So, well, it is usually said that flow matching was proposed by these authors of these two papers, but on the next lecture, I will actually give you one more reference about one interesting paper from even 2021, when this concept was proposed, but no one actually knows because like these papers are the most popular. So if after lecture you would like to consult more about flow matching, yeah, you can take a look at these two first papers. And my today's exposition will be primarily related to second paper because these two papers, they give different view on flow matching, which is in many aspects equivalent, but in my view, this second view of rectified flow paper is more transparent, more easy to understand. But at the same time, the view on flow matching which is given on the first paper is more closely related to standard diffusion models. Okay, before discussing this, let's do the following. So let's recall some basic mathematical concepts which we'll need to understand our today's presentation. So the main concept is the concept of vector fields. Yeah, so we are going throughout today's lecture, we're going to consider the concept of just time-dependent vector field in d-dimensional Euclidean space. So basically, what is that? Basically, we assume that we work in d-dimensional Euclidean space. So this is just like two-dimensional picture for better understanding, yes. And vector field, which also depends on time, Yeah, so this is a function of two variables, of a point in space and time moment. From time goes from 0 to 1. And for each time, yes, for each point, it assigns some vector, some speed vector, where we kind of points towards the direction where we should move. Yes, if we have a vector field, what we can do? We can define the movement of some point along the vector field. So basically, if we put some mass unit point in this vector field, how it will move, if this vector field will be its speed vector, which defines the movement. Yeah. This movement along the vector field is usually described in two forms, so in integral form and in differential form. So roughly speaking, if we put some point into the vector field at time moment 0, and we say that at time moment t or tau, this point moves according to the vector field at the current point and current time moment, then this movement of a point along the vector field defines some trajectory. Yeah? To get this trajectory, in practice, you can do this integration. And this integration in practice is usually, of course, done by some numerical approximate schemes, because for like general vector fields, you cannot obtain an analytic expression of this trajectory. So just similar way as we discussed for diffusion models, how you model trajectories by Euler-Maruyama scheme. Here, this is usually modeled by some solvers. One simplest version is the Euler solver, which is just simple time discretization of the trajectory. Yes, so to move to the next point t plus delta t at time moment t, yes, you need to take the point at time moment t and just add to this point current speed vector multiplied by this delta t. And of course, here, just as the same way as I discussed for diffusion models, the question is, okay, which discretization should we pick to accurately model this vector fields, this movement along the vector fields? Yeah. Okay. So now that when we recall this concept of just basic vector fields, movement of a point along the vector fields, we can also define the following thing. For every initial point, say z0, yeah, we can define the point z1 as a function of z0, basically the end of the trajectory when the point moves along this vector field. Of course, from the mathematical perspective, well, to define this object accurately and correctly, yeah, you need to make some assumptions on this vector field, for example, Lipschitzness and so on. Let's not discuss this in detail, just not to make the lecture too much complex. Just for now, we'll assume that the vector fields are good enough so that we can do this integration from the mathematical sense correctly. So this is like well defined. Okay, and what is the main idea? The main idea of flow matching, actually not even flow matching, the idea of flow transport. The idea is as follows. Suppose that you have some input probability distribution. For example, it can be noise distribution, yeah, just as in diffusion models. And you would like to create from this noise some data distribution. Yeah, for example, P1 will be the data distribution, for example, as here, yeah, the distribution of, I don't know, faces of people, yeah, given by data set in practice, of course. What is the idea? The idea is, let us do the following. Let us try to find some time-dependent vector field, V, such that, roughly speaking, informally, if we push the probability mass of our input distribution according to this vector field, then at time moment 1, we will obtain the distribution which we want to model, the complex data distribution. What does this mean in more formally? Yeah, so if we have some random variable x0, for example, yeah, and it is distributed as our input distribution, what we would like to have? We would like to consider the random variable x1 of x0, which is basically this integration, yeah, the result of this integration over our given vector field. And we would like to have this result of integration, x1, to be distributed as our target distribution, like our data distribution. And if we manage to find such a vector field that satisfies this property, yeah, then we kind of solved our generative modeling problem, so that we will be able to take new samples from our input distribution, integrate them, so move them according to the vector field, and the new obtained generated samples will be from our target distribution that we would like to model. Yeah, and yeah, so the question is how to do this, how to find such a vector field, such generative vector field, yeah, because it tries to generate our data distribution from some input simple distribution which we can easily model. And this is what we are going to discuss. In fact, first of all, what we should take into account, yeah? Suppose that we have found such vector field which maps the input probability distribution to the target probability distribution. But in fact, there might exist several such vector fields which map one probability distribution to the other. Yeah, roughly speaking, each vector field, what it does, actually it defines some sequence of probability distributions showing how your probability mass moves according to this vector field, right? And the question is which one to choose. So should we choose like this vector field and this sequence of probability distribution to do data generation, or should we choose this sequence? A short story is that ideally we would like to choose sequence of this type. Why? Because originally we started from straight trajectories. Yeah, so we want to obtain straight trajectories for data generation because these straight trajectories are easier to model. But, well, obviously in this toy two-dimensional example, obtaining straight trajectories for this case is much more complex than for this case. But the question is, okay, can we somehow formalize it what we want? The answer is yes. We will talk it in the next part of the lecture, but for now, let's do the following. Let's first of all try to find some vector field which interpolates from one distribution to the other distribution. One quick comment. So from the mathematical perspective, yes, this movement between the probability distributions can be described by the well-known continuity equation. Yeah. In my lecture, I do not give a lot of details related to this because they overcomplicate the understanding. But most of standard theoretical results which are proved in this flow matching paradigm, they are usually proved using this continuity equation, and you can take a look at these two first papers which I mentioned at the beginning because I actively use them for proving something. So, okay, let's do the following. Let's first of all think about the following question. I'm asking the question, how can we find a vector field which moves one probability distribution to the other? I've told you that every vector field which does this, it defines some sequence of probability distributions which interpolates between two probability distributions. Yes, like this sequence, yeah, or this sequence. Let's do the following. Before finding the vector field which produces this sequence, let's try to somehow define the sequence, because even just defining the sequence of probability distributions which somehow interpolates between them is not a trivial task. And we are going to do the following thing. Yeah? We are going to first define some sequence of probability distribution which interpolates between input distribution and target distribution, and then find some vector field which produces this sequence. Okay? So one of the most natural ways and very simple ways to define some sequence of probability distributions which interpolates between two given probability distributions is the so-called linear interpolation of points. How it is constructed? So suppose that you have two random variables, x0, so just random samples from input distribution, and x1, random samples from target distribution, and assume that they are independent random variables. And your goal is to construct some interpolating sequence between these two probability distributions. How it is constructed? Basically, what we need to do, we need for every time moment t from 0 to 1 to define some probability distribution. Yeah? This is done the following way. You take your original points x0 and x1, independent random variables, and define a third random variable xt, which is a linear interpolation between these random variables. And you say that the distribution of this random variable xt will be your interpolating distribution pt at time moment t. So if you take like t equal to 1/2, then you just take 2 points from input and target distribution at random, average them, so obtain some average point, yes. And this point will be a sample from your intermediate distribution at time 1/2. And you can do this for any time moment t. Well, I would say that it is kind of obvious that this sequence of probability distributions which can be constructed this way, so basically this sequence is the sequence of probability laws of distributions of these random variables xt. It gradually interpolates from p0 to p1 because, well, if you take limits of t from 0 to t goes to 0 or t goes to 1, then obviously you obtain p0 or p1. Yes? Okay, so this is a very, very simple and straightforward way to construct interpolation between two probability distributions in the sense of the sequence of probability distributions. And one very important practical aspect of this construction is that in practice, we do not have the distributions themselves, we have only samples from these distributions. And this construction allows obtaining samples from intermediate distributions using samples only, yeah, because we need in this construction only samples from these probability distributions. Okay, the main question is, we constructed some sequence of probability distributions which interpolates from, for example, noise to data. Yeah? But this thing, it cannot be used for generative modeling, yeah, because it does not give some construction. How can I take sample from input distribution and produce sample from some target distribution? Yeah, because this construction, it builds kind of trajectories only when you know some start point and end point. Yeah. The question is, can we find some vector field such that if we use this vector field and move the probability mass of this distribution according to its vector field, we will obtain this sequence of probability distributions, and in the end, we will generate our target probability distribution. Okay, so how this is typically done? This is actually one of the main slides in the presentation, which explains how can you construct a vector field which produces this sequence of probability distributions which was defined on the previous slide. What you need to do? The main idea is as follows. So you solve the following regression problem. So you want to find a vector field V which minimizes time-dependent vector field which minimizes this objective, this regression objective. What it does? Basically, it does the following. So we sample 2 points from input distribution and target distribution independently. Then we sample random time moment from 0 to 1. And then we do interpolation of these 2 points, so obtain point xt. And then we do the following. So, okay, we have 2 points, x0. We have point x1. we sample random time moment t and sample some point xt. Not sample, but average these 2 points and obtain sample xt. And then we regress our speed vector v onto the direction of this line from which this point came from. Yeah. The main idea is that when we do this regression, yeah, what we obtain in the end. In fact, the optimal solution in this regression is not the direction of this line x1 minus x0. Actually, it is a different thing because what we do, what I just said, we take some point xt and regress on this direction. But the same point xt at the same time moment t might have appeared on different pair of points x0 and x1 prime. So when we do this regression, in fact, we kind of average all the movement directions for a point, and we average all directions of interpolating lines which contain this point. Yeah. So in the end, as it is widely known, when you solve like regression with quadratic laws, your optimal solution in the end is some average vector, average in the mathematical sense, with respect to like probabilities of all these interpolating lines. So then it is known that, okay, when I solve this problem, this regression problem, in the end I obtain some speed vector, v star, for example. Yeah. The question is which properties it satisfies. Yeah, because okay, just right now I just said, okay, let's do some regression. Why it is meaningful? Why it leads to something reasonable, can be used for generation, so on. In fact, it may look even somehow contradictory that this vector is somehow meaningful, because what I do some like averaging, so I kind of destroy some information in some sense. Yeah, but the main property which this speed vector, the optimal solution of this problem, satisfies is that if you consider this system of equations, so basically if you take point x0 from initial distribution p0 and you solve this ordinary differential equation, so if you move this point according to this obtained learned vector field, then you will obtain, in fact, the same sequence of probability distributions which was originally designed with our like interpolation. And furthermore, this sequence will be meaningful from the practical sense, because now you will be able to do generation of new data, yeah? Because you will be able to take some point x0 from input distribution p0 and just integrate it, and you will obtain some point at the support of your target distribution. This can be formalized actually in the following sense. So roughly speaking, you have original construction with two distributions, interpolation between them, and the sequence of probability distributions which does this interpolation. This sequence after flow matching is not changed. But you obtain some vector field which basically defines the same movement in the sense of the same sequence of probability distributions. In particular, the end point of this movement will be the target distribution P1. And furthermore, this vector field which we search for, yes, which we want to find to do generation, even has a closed form. Yeah, so there is some formula how you can, well, theoretically compute this vector field from your data. Basically, what is that? It says that, okay, to obtain your vector field, which we search for by solving this regression, we need to do the following. We need, if we want to find this vector field at point xt and time moment t, then what we do, we take all directions x1 minus x0 as on the previous slide. Yeah, so all directions 1 minus x0, which goes through this point. Yes, at the given time moment. Yeah, and given this point, we sample all the trajectories which go through this point and average their direction. And the problem here is, well, what you may ask now, yeah? This theorem, yeah, it provides some closed form for this vector field. Then why on the previous slide did I told you that let's solve this regression problem? If we have closed form, why do we need to learn something? Yeah, why not to just use this closed form? The main point here is that this closed form solution is intractable. Why it is intractable in practice? It is intractable because to compute this expectation, we need to sample for a given point xt at which we want to compute this speed vector. We want to sample the endpoints of the trajectory from which this point came from. But the problem is that in our construction here, we cannot do it. We can sample only intermediate point, given endpoints, but we cannot do the reverse thing. We cannot like pick some point and say, okay, give me all the trajectories from which this point comes from at this given time moment. And this is the problem. So because of that, this theoretical vector field is intractable. But fortunately, one may prove that this objective, which I gave you several slides ago, has the same minimizer as this optimal vector field which we search for. Well, I'm not proving this here on this slide. This is more or less standard fact. You can take a look in the papers, but the main point is that this vector field, which we search for, yes, is intractable. But it can be solved and found using this regression problem. This is just like L2 regression. Yes, and in this regression, everything is kind of tractable in the sense that we can sample points from our input distribution, for example, noise distribution x0. We can sample points from our data distribution. Well, of course, in practice, this is just some empirical data set, not the entire distribution. But anyway, and we can sample random time moments. So all this is computable for samples. And in practice, what people do, how they solve it, they do the following. They take a neural network as this function v, as this speed vector. A neural network which takes as input a point xt and time moment t, and outputs some speed vector. So basically it is a neural network which takes d-dimensional Euclidean input, time moment, and outputs another d-dimensional Euclidean output, which is speed vector. And they just solve this regression problem. How it works? So in fact, it works the same way as I told you on the previous slide. So we just replace this expectation by Monte Carlo estimates because we only have samples from our target distribution P1 and our input noise distribution. Yes, and we solve this using some standard deep learning methods like stochastic gradient descent variants like Adam optimizer and something like that. Yeah, and at the end of this training, well, if your data set is sufficiently big, if your neural network is sufficiently expressive and you train for enough amount of iterations that you converge to some solution of this problem, yes, and this solution can be used for generation. Let's see how it works in practice. So this this shows just some generation path of the model. So first line is just testing this flow matching model on just generation of data set of like cat faces or some, I don't remember. It's like animal faces, high quality data set as far as I remember, yeah? So this is how the trajectory of your generation looks like. You start from noise, and then you apply your speed vector gradually, yes, and then you come to final point, generated point. What is shown, and this is the same, but for, I guess, CFAR dataset. What is shown on the second lines here and here? Basically, it shows kind of trial to simplify the generation process. In which sense? So suppose that you integrated your trajectory up to some time moment. For example, like this, 0.025. And you do not want to further integrate your trajectory. You would like to do a very rough approximation of your trajectory. You would like to take your current intermediate point, its speed vector, and just jump to the final time moment. The question is whether it will be a good or bad approximation of your true trajectory. So this example, it shows that obviously it will be a bad approximation. So if you just try to do one-step generation, so you start at some noise and just try to jump by your current speed vector directly to the end point, then you obtain something very blurry. Of course, the closer you get to your final time, the more accurate your like endpoint jump approximation becomes. But what this example shows? This example, in fact, shows that the trajectories which are obtained by this flow matching method are not as straight as we originally wanted. Yeah? Because one of things when I started this lecture, I was talking about, okay, let's get some straight trajectories. But actually, nothing in this construction, which I demonstrated here, motivated the trajectory to be straight. It was just some interpolation by some vector field. Okay. This is also some another example that this flow matching paradigm, in fact, can be used not only for noise to data generation, but data to data transformation as well. So this is from the authors of, I guess, Rectified flow paper, which shows that you can solve this domain translation problem as well, like when your input distribution, like P0 is like the distribution of like cats, for example, is here, yes, and your target distribution is distribution of wild animals. Yeah, you can do this manipulation like cat to wild and so on. Okay. But one thing which we obtain here is, in fact, as I already told you 2 slides ago, the trajectories which we wanted to model are not as straight as we originally wanted them to be, right? Furthermore, this can be seen on this toy example. So what this toy example shows? This toy example shows that how flow matching works when you try to work with 2-dimensional distributions and you try to map your input mixture of Gaussians, this purple mixture of Gaussians, to your target mixture of Gaussians, which is here in red. And this path, they show the learned path of the flow matching model. How do they look like? This is like in high dimensional case, yes, so this like previous was in high dimensional case when we applied to image generation, so our data dimension was very high, like it was, I don't know, 128 by 128 by 3 like RGB pixels, yeah? And this is like just toy example on 2-dimensional space. So your data dimension is 2 coordinates, like this coordinate and this coordinate. And what do we see from this toy example? From this toy example, we see that actually the model that we learned has very bad trajectories in terms of straightness of this trajectory. They're not straight. Yeah, you see that to generate data, you need to kind of first go this way, then do quite high rotation and follow this trajectory. So this is not what we actually wanted. Yeah, we wanted to obtain some more straight trajectories, and this construction does not provide it out of the box. Yeah, so this, in some sense, is similar to like diffusion models. Yeah, in diffusion models, when I started the lecture, I also demonstrated use this kind of curved trajectories. Well, maybe these are a little bit simpler trajectories because there's the trajectories by just without noise, yeah, with ordinary, obtained with ordinary differential equations. But the question is, can we even further make these trajectories more straight? Yeah, so that there will be no this like curve, so that we can go directly from one point to another point. The answer is yes. And one of the methods which appeared in 2023 for this is called the rectified flows. Basically, what was the idea of rectified flows? The idea is follows. So suppose that you have your flow matching model. So you solved your flow matching in the sense that you learned your vector field between input distribution and the target distribution. Yeah? And let us call the result of this optimization procedure by V1, like vector field obtained after like learning flow matching for the first time. Let me call it this way. Yeah. What is the main idea? The main idea is that theoretically, yeah, according to the theorem which I showed several slides ago, this learned model satisfies the following principle. The principle is that if you take some point from input distribution and integrate it according to your learned vector field, V1, then you will obtain some point x1 of x0, and the distribution of these points obtained by this way by integrating different trajectories from P0 will be the true distribution P1. Roughly speaking, what we can do with this? So roughly speaking, we obtain some kind of transport between P0 and P1. The main idea of rectified flow model is to use this obtained transport to further improve the flow matching model and the straightness of the trajectories. How it works? It works the following way. Okay. At step 1, like V1, you just learn your flow matching model the same way as I described several slides ago. But then what you do? Okay, you have your interpolation. You learn some model, some vector field, and it defines some transport from P0 to P1. Then you do the following. You forget about your dynamic part of your transport. You do not care anymore how this model performs this transport. You care only about the input point and about the end point of this transport. And the property of this pair of x0 and x1, that it is actually a coupling of two probability distributions. Yeah, in the sense that this distribution of pairs x0 and x1, yeah, it has marginal distributions. Per x0 it is p0 and per x1 it is p1. And this property can be used to further train flow matching models. How? The idea is the following. Let us take these pairs obtained after the integration of the trained model after the first step and use these pairs. These points and these points are the same as these points and these pairs. Use them to construct a new interpolation between two probability distributions the same way as we did here, but here we considered independent samples from x0 and x1. And now we consider dependent pairs from x0 and x1, and this dependence is defined by our previously trained model. Yeah? And using these dependent pairs, what we can do, we can train another flow matching model, yeah, with the same laws, but different construction, how these pairs are obtained. Yeah, so what changes? So if we go back to this slide, what we do? We sample points x0 and x1 from input and target probability distributions independently, sample time moment, and sample this interpolation point and do this regression. What we do now, we sample point x0, and now we sample point x1, but not independently, but dependently, using the previously trained model. So what we sample point x0, integrate the trajectory, obtain point x1, and then we put it as like a second point in for point x5, for x0, average these points according to time moment t, obtain this intermediate probability distribution, and solve this regression. Yeah? Then after this, we obtain a second trained model, second trained vector field, which does also some transport of P0 to P1, but in fact it does the transport differently, because this sequence of probability distributions which appears in this transport is now becomes different because it was constructed in a different way using dependent pairs. After that, we can repeat this process. So we can just again take this model V2, say that, okay, we have x0, we have some integration of x0, obtain some target point, and we can again repeat many times. And at this point, you may ask, why do we need to do this repetition? Why it helps us? In which sense it helps us? Surprisingly, there is a theoretical result, which is here formulated in informal way, but roughly speaking, it says that after this iterative flow matching procedure, when you do this flow matching step by step on top of every previous model, you obtain a new model each time, yes, and the straightness of the trajectories of this model becomes better and better. Yeah, it can be formulated like well, right now I say like straightness a little bit informally, but in the original paper, for example, the authors formalize it like by some formula. What is this means by like straightness actually, yeah? And the main point is that this is the result of original flow matching in two-dimensional space, as I already showed you, yes? This is what happens after one training of flow matching on top of previous flow matching, and this is like after several repetitions, what you obtain a model with straight trajectories. Why this is good? Because you can just model it in one step, model such trajectories, because you just, if you want to go from some point in input distribution to some point in target distribution, you need just to consider the speed vector and just do a very big jump, because you know that anyway your trajectory is straight. And yeah. Okay. Furthermore, the authors did some experiments showing that to make the trajectory straight enough for practical use, yeah, for fast one-step generation, it is just enough to do 2 or 3 iterations of this flow matching. Yeah, so it kind of, the convergence there is exponentially fast in the sense of this straightness notion which the authors propose in the paper. But everything is not perfect, unfortunately. So what is the main problem? The main problem is, well, theoretically this procedure is really good. Yeah? It allows you to obtain straight trajectories, which in the end can lead to fast one-step generation in your model. But the problem is that in practice, everything is not as perfect as theory. First of all, when you train your model, your flow matching model, on the first step, what you obtain? You obtain some approximation, right? Approximation from many perspectives. First of all, from the approximation perspective, that you train a neural network which has finite capacity. Yes, you train your model by stochastic gradient descent, which is not necessarily something which converges to the true global optimum. And furthermore, you train using empirical samples. So your data set is finite. You cannot train on the entire true data distribution, yeah, because you only have samples in practice. So, which means that your model, which you obtain after the first step in practice, is an approximate model. It does not model the true probability distribution of data. There is some error, roughly speaking. But when you do the second step of flow matching, what we do? In fact, you already use this approximate model. Yeah, we do not use the true data. Yeah, because we need the coupling which was obtained by the original or by our trained model. Yes, so roughly speaking, when we do the second step of flow matching, we already train on synthetic data, which has the same problem. First of all, there is already some error. Then after training, we further increase this error because just we train on synthetic data. And this error repeatedly accumulates. Yeah? So this means that in practice, this procedure is not very useful if you want to obtain if you want to do many iterations, because you will just accumulate the error. But fortunately, the authors demonstrated that in practice you just need like 2 steps, and the trajectories will be already straight enough for generation. But there is one more problem with this scheme. Yeah, with this scheme. The problem is as follows. So, okay, when you do your first step of flow machine training, it is so-called simulation free. What does this mean? This means that you do not model any trajectories of your model. Yeah, you just take input point, you just take target point, and you just interpolate them and do some regression at this intermediate point. But on the second step of flow matching already, and on the next step, the problem of simulation appears. Basically, to obtain for input point x0 some point in this target distribution, you need to integrate your trajectory, which is very complex, because like you need like 100, for example, of steps of modeling your movement along the vector field. Yeah, so this is complex. So each iteration from second to the last iteration of this procedure is not simulation free. Roughly speaking, you need to use your previously trained model and integrate its trajectories to train the next model. So where this appears? This appears in this loss. Yeah. So to obtain this point x1, which is like a pairing point for x0, you need to do integration along your trajectory of your previous model, which is challenging and makes the next steps of this procedure more challenging than the first step. And this procedure, in fact, is usually called the rectified flow procedure, because kind of on each step you try to more and more rectify or improve your flow matching vector field and make it more straight. And this shows that in practice, actually, 2 steps of this rectified flow procedure are usually already enough to obtain reasonably straight trajectories. So this is the original thing which I already demonstrated you. So what happens here? If you, for example, start generation at some point, you can of course integrate the vector field. Yeah, but you can do the following. You can start at some point, some noise, and try to do a big jump. If your trajectory is not straight, then this big jump will be something just random. Yeah, it will output something. So this is what happens after you change just one flow matching. Yes, but if you do rectified flows, like train model of flow matching, then train again the model on top of this model, then already even just one step generation from time moment 0 to jump to time 1 becomes quite meaningful already. Yeah, so it's not like something which is very blurry, which is of reasonable quality. Yeah. So roughly speaking, this works. Yeah, this is like what is shown on these second lines. Yeah, so at some point xt, you would like to do a big jump to the final time moment. Yes, and this first lines is just when you try to integrate accurately your trajectories, but this is usually complex. Yeah, because you need to model your entire trajectory. It is obviously much better if you just do like one step generation, because you need to apply your neural network only once. Basically, well, I think these are some more slides, yeah, showing some examples. Yes, and columns here show just, these columns are a little bit different from what was shown previously. These columns show that the initialization, yes, for your sampling, and this shows the result of integration of the trajectory with different amount of steps. So discretization, like if you do very big discretization, your result is very good for one step flow matching. But for rectified flows, yes, you do not need, for when you do like training of model on top of previous model, you do not need that much amount of integration steps. You can reduce it to something which is much smaller. So the generation will be much faster. Okay. And furthermore, in 2023, these guys, the authors of Rectified Flows, they published a paper when they showed that this paradigm of flow matching can be used for something which is like slightly different from what I was talking to you about. They showed that you can apply this paradigm to distill diffusion models. Yeah, so in diffusion models you do generation by stochastic differential equation. What they showed that you can kind of apply flow matching or rectified flows on top of already trained diffusion model and make it faster as well. So you can do one-step generation in diffusion models with this technique on top quite easily. But since then, a lot has changed in the field of generative AI. So although this was just 3 years ago, yeah, because a lot of more advanced techniques for diffusion distillation appeared. But nevertheless, this was very important step in just the field of generative AI for images. Stable diffusion model at 2024, I don't remember, it was Stable Diffusion 3, I guess, was built on this concept of flow matching and rectified flows, but it was not exactly as I described you today. There was some like technical improvements on top of this flow matching, for example, different schedule for trajectories and so on. Yeah, but the short story here is that it scales, and furthermore, it is now widely used as in many modern large text-to-image models. For example, some part of Kandinsky model is based on flow matching. Yeah. Okay, and final part of our lecture is just to show that this thing has some extensions, and one of such extensions is flow matching with general transport plans. What is this basically? Basically, if you take a look at what we have discussed so far, yeah, originally we started from flow matching when you sample your pairs of like noise and data independently, yes, and train your flow matching model. Later we discussed about rectified flows. This is an approach when you sample pairs for your training of your model, like x0 and x1, dependently using some previously trained flow matching model. So this naturally raises the question whether we can do something more general and train our flow matching model using just arbitrary dependence between 2 points, x0 and x1. Yeah? For example, not necessarily independent case and not necessarily the case when these pairs x0 and x1 are produced by previously trained model. And the answer is very simple. Yes, to train flow matching model, we can take any dependence between pairs x0 and x1 in input and target distribution. So in mathematical language, this is usually called coupling or transport plan between two probability distributions. Yeah. What we do, we do the same as before. This is the same theorem, the same statement, but with one modification shown here with blue. So previously we took pairs independently, x0 and x1. Now we can take pairs with any dependence between them, where this means that this joint distribution of x0 and x1 satisfies the property that the distribution of x0 is exactly p0 and distribution of x1 is p1. And you can train your model. So what will change? What will change when we'll use arbitrary dependence between pairs from input distribution and target distribution? In fact, the interpolating sequence of distributions will change. Yeah. And you may ask, okay, why this may be useful? Why it may be useful to consider general transport plans? The answer is as follows: that there are several transport plans which are not very hard to compute, but they may be useful in practice. So in terms of computation or algorithm optimization, yeah, you do the following. You just, when you train your model, replace only one thing. You sample pairs dependently. That's it. But the question is, okay, which transport plans, which pair dependencies can be used? And the short story is one thing which you already know is independent transport plan. When x0 and x1 are just independent, you can use it. But the trajectories which you obtain are quite curved and not always useful in terms of generation, because it may require a lot of evaluations of your base model to generate new data. So one other variant which is usually considered is the so-called data-based plan. What is this? So suppose that you solve some problem when you want to map points from x0 to x1, and you know how to map them. So you are given pairs for training. This sometimes happens in some paired training problems, which we'll discuss in the next lecture. For example, when you solve like image super resolution problems, when you have input image of low quality and you would like to obtain an output image of high quality. And you, in fact, you have these dependent pairs already. Lower resolution images and high resolution images. You can put them to this training algorithm. But there is one very, very important aspect, that when you solve flow matching with some transport plan, you do not necessarily preserve the original dependence between pairs. So it may break. This should be taken into account. But in some problems, it is not a really big issue. It works. But another thing which people invented and which is, well, sometimes used nowadays is a very, very simple way to build some couplings between two probability distributions. And this way is called the mini-batch optimal transport coupling. What is that? Basically, it works the following way. You sample a batch of points from your input distribution. You sample a batch of points from your target distribution. And between these two batches, you solve the so-called discrete optimal transport problem. Roughly speaking, what it does, it tries to find some optimal assignment between two batches, so that each point in one batch will be as close as possible to the point in another batch on average. And this is in practice done by some so-called discrete optimal transport solvers. You can just use out of the box from, there are many libraries for this, like Python optimal transport and so on. And the main idea of this is that when you use this kind of more optimal couplings, when like point corresponds to more closer point in the second distribution, then in the end, your transport plan yields more straight trajectories. So this is an example when you train flow matching, standard flow matching with independent pairs between mixture of Gaussians and two-dimensional distribution. Then you see that the trajectories are very, very complex. They are somehow curved, and I don't know, it's even hard to parse what is going on here. But if you train it with mini-batch optimal transport coupling, the trajectories become much more straighter and easier to model. Of course, this has some limits. So these mini-batch optimal transport couplings, they work in two-dimensional space, but when you scale it to some image distributions on high-dimensional space, they are not always good. But there are some recent papers showing that even in this case, you can improve much better, you can obtain much better performance. So finally, just to conclude the lecture, I would like to say the following things. So first of all, previously we discussed that when you do rectified flows, you have this problem that you do this error accumulation step by step, and each next iteration is not simulation free, and there are some issues that this overall procedure is complex, it accumulates errors and so on. Can it be somehow solved in practice? So can you design some kind of flow machine which will immediately yield you straight trajectories? The short answer is yes. And actually this is our paper, the paper of my group from 2 years ago. We showed that in flow matching you can actually design an algorithm which will yield straight trajectories in just one flow matching step. But it unfortunately requires using some special class of neural networks called input convex neural networks, which are not very expressive in practice. What we are going to discuss on the next lecture. On the next lecture, we are going to discuss extensions of this flow matching, which are, I would say, even more complex. it is called bridge matching. So roughly speaking, bridge matching is flow matching with some additional noise components. So in this sense, this extension is very simple and natural. And this extension is widely used for so-called domain translation problem. When you want to apply generative modeling, not only to data generation, but when you would like to apply generative models to certain data-to-data transformation, like image super resolution, deblurring, and so on. And we'll discuss this during the next lecture. And yes, these are some preliminary examples from the next lecture. I think I'll skip this because we're going to discuss during the next lecture. And just one final slide to conclude that today we discuss the flow matching, which is the modern paradigm in generative AI. People usually study flow matching like more than diffusion models because it's much simpler. Yeah, you have very simple regression objective. No these like very, very complex formulas with diffusion coefficients and so on and so forth. And it works. This is the main point. Second point is that in flow matching there are some ways how you can make straight trajectories. Yeah, by rectified flows or by using special transport plans, yes, such as mini-batch optimal transport coupling and so on. Yes, and this flow matching, in fact, is very, very closely related to diffusion models, although from our today's lectures, this may not be very transparent, this relation. Nevertheless, next lecture, we're going to discuss the extension of flow matching, diffusion bridge matching, which is more closer to diffusion models, I would say. And okay, so yeah, be prepared. So that's it. Questions?
So thank you very much. I missed a moment. How do we create these pairs of x0 and x1 primarily on the first step?
On the first step, you just take independent noise and independent data. So randomly. Just take random pair from data, random sample from data, random sample from noise. So this is your pair.
Okay. Thank you.
Thank you for the lecture. My question is, in the beginning of the lecture, you mentioned conditional modeling with this type of models, how it's implemented.
Yes, so this lecture was primarily about unconditional generation. But I would say that in conditional generation, what you do, you just train the same objective, but in your model, you just add one more input. We will discuss this during the next lecture, because during the next lecture, there will be a specific part related to conditional diffusion bridge models. I think it will be more clear during the next lecture.
Thanks.
So one more question, please. Do exist an approach when we choose not only one x first, x1, but several x1 but close to each other, and then repeat few times? So yeah, this method, this approach, and then take the average result, I don't know, average x1 like that.
Well, I would say that there exists such extensions, probably, yes. So there is this framework of flow matching is very general, and one of the papers, well, I think yes, and this construction is very general, and you can take a look at this paper. It provides, I think, what you ask for, where it is. Like this third paper. You can take a look at third paper. It just provides very general construction, even more general than we discussed today.
Okay.
Thank you for your lecture. In the very beginning, you told that the path of diffusion is not linear, and for objective you used linear interpolation. Is it work for any multinomial function, or can we use, for example, function of power 2?
Yes, you mean how to construct interpolation?
Yep.
Yes, you can construct interpolation by just general interpolant which satisfies certain criteria. This linear interpolant is just the simplest version. So this more general framework is called like stochastic interpolants, which I told at the beginning of the lecture. So yes, you can just Google for paper like building normalizing flows with stochastic interpolants or something like that.
Thank you.
You can even learn these interpolants if you really want, like not just to construct, but learn directly.
More questions?
And how does it affect the quality of predictions when we're constructing some generic interpolant instead of linear one?
Well, usually linear works, well, usually there is not very much gain from considering general interpolants. So usually linear is one of the best, and one of its best extensions is when you just consider linear interpolant with some noise, kind of stochastic interpolant, but still linear. So yeah. But in fact, diffusion models, they can be viewed as flow matching with certain interpolants actually.
Thank you.
And why then the linear interpolation works so good? Is this because of supposal, because of an Euclidean space that we suppose we have?
Yes, so I think it just works for two reasons. First, it is the simplest one, and second, it is like the most well-tuned. Like the community mostly improves models specifically for this interpolant. This is why it works better, yeah? But if we talk about non-Euclidean geometries, for example, when some like, you know, manifolds like groups of rotations and so on, this flow matching concept, of course, is extended to these groups. Like you can use more general interpolants there as well, which take into account the geometry of the space, roughly speaking.
Like geodesical interpolation?
Yes, exactly.